Hello, everyone. Today we're going to try and make sense of electron configurations by introducing term symbols. So, term symbols are a condensed way of talking about electron configurations that summarize the spin, the orbital angular momentum, and the total angular momentum. So, this is done by using essentially a combination of three symbols. So we're going to start by focusing in on the symbol that dominates the term symbol, actually what gives it its name. And that's going to be the letter designating the total orbital angular momentum. So in case you need a refresher, this would be if L equals 0, an S state, if it equals 1, a P state, so on and so forth. So this is going to be one of the features we'll focus in on, but we also have two other components. The next being the multiplicity, which as a reminder is twice the spin angular momentum quantum number plus 1, where again, S is our total spin angular quantum number. So this would be a singlet, doublet, triplet, quartet, so on and so forth. So these two give us a lot of information about whatever atom we're talking about. But we also need to figure out exactly how these two terms interact. And so we finish off our term symbol with the total angular momentum quantum number, or J. That said, it is not uncommon to see term symbols reported just using the multiplicity and the total orbital angular momentum and leaving out the J value. So let's go ahead and try and use what we know about these three values to construct some term symbols for some species we know. So let's start off with a fairly simple case. Sodium. So if I have sodium, I have a closed shell neon atom plus an extra electron in the s orbital. So this hopefully shouldn't be too bad, as I can ignore everything with a complete subshell. So we can more or less just ignore the neon. And when we're talking about term symbols, we really don't care about n. So for our purposes, I just have a single electron in an s orbital. And if I have an s orbital, this has no orbital angular momentum. So my total orbital angular momentum is 0. So we have an S state. Woohoo! So then I have a single electron, which makes determining the total spin fairly straightforward, as it has to be 1/2, which gives me a multiplicity of 2, or a doublet state. So now I have most of the term symbol done. All I have left is the J value. Well, we get very lucky here because since I have an S state with no orbital angular momenta, this means we have no angular momenta coupling, so J has to be equal to S. So J equals 1/2 as well. So then we can go ahead and take these three components together, put them in a symbol, and we have a 2s 1/2, or a doublet S state with a total angular momenta of 1/2. So if I'm dealing with one electron, it's not too bad. And we can extend this idea to if I have aluminum, where I have a full set of core electrons in neon. I have a full subshell, s subshell, with 2 electrons in the s orbital. And then I've got one last electron in my p orbital. So we can ignore our full s subshell and the core electrons like we did before. And so for our purposes, all we have is one electron in a p orbital, which again makes our total orbital angular momenta fairly easy to deal with, as it has to be 1. So this gives us a p state. So we now have our central symbol. And again, with a single electron, we again produce a doublet state. Now, where this gets a little bit trickier is that my J values mean that I can have spin-orbit coupling, where these two add together, or they're opposed in different directions, and I'll take the difference. So for this complex, J can either be 1/2 or 3/2. So now we're a little bit more complex as we've got two possible different term symbols. A doublet P with a 1/2 total angular momenta, or a doublet P with a 3/2 angular momenta. So we aren't limited to a single term symbol for a given electron configuration. Now, if I'm dealing with a single electron, figuring out how my orbits and spin interact isn't too bad. But as I warned you last time, things get a little bit messy as soon as I put two electrons into an incomplete subshell. So things get a bit messy once I reach silicon, which has two electrons in an S subshell and two electrons in a P subshell. So in order to try and figure out our term symbol for this species, we have to write out all of the possible electron configurations, or as P chemists like calling them, microstates. And when we do this, we're going to want to write out our total orbital and our total magnetic quantum number and our total spin magnetic quantum number. So our orbital and spin contributions to the magnetic values. So again, when we're doing this, I want to remind you that orbitals on the left side are going to have an m sub L of -1. Orbitals on the right side have a value of +1, the middle orbital 0. And you can continue this idea as we've done before for a D system where I'd have 5 electrons ranging from -2 to 2. And again, if an electron is pointed up, we'll give this an m sub s value of +1/2. If it's pointed down, -1/2. So we're going to go ahead and add together our m sub L and our m sub s values to figure out the total. So in this case, I have 2 electrons in the -2 orbital, so I'll have a total m sub L of -2. And my 2 spins are paired off and should cancel out, so I'll have no net m sub s. So I'm labeling this as a -2 and 0. So this is a fairly straightforward state, but now I have to count all of the other possibilities. So be very careful when you're doing this, and finding a sequential pattern that works for you is usually a good idea. I like starting with a double filled on the left and then moving one electron over to the right. I like to start with a spin up electron, so I can have both my electrons pointed up and then either in the second or third orbital. Well, since I've got 2 electrons pointed up, this is going to give me a m sub s value of 1, or essentially an effective triplet state. But in this case, my m sub L value will be -1, because -1 plus 0 gives me -1, and this one will be -1 plus 1 gives me an m sub L of 0. So now I have 3 states. Well, I need to continue my counting, so an easy thing I can do is go ahead and take these 2 electrons and then flip the direction, which will give me essentially 2 states with an m sub s of 0, and I haven't changed my m sub L at all. So now I've calculated a total of 5 possible microstates, but we've just started because I haven't had a single case where my first electron points down. So I can regenerate these 4 states where my first electron is pointed down and I leave everybody else the same. So when I do this, my m sub L values won't change. But now my m sub s values will decrease by 1. So as I go from a value of 1, this now becomes 0, 0, and then in these cases, everybody's pointed down, so I have a -1 value. So this is all the possible configurations where I have 1 or more electrons in the first orbital with a m sub L value of -1. So now I can pair up 2 electrons in my central orbital with an m sub L of 0. And this case, I have a paired set of zero orbitals and a paired set of electrons. So this guy has no net magnetic number. So we have another 0, 0, making it our third yet. So now I can move one of these electrons over. Again, I'll take the one electron pointed down, and it can be pointed up or down in my third orbital. Both of these cases, I will have a net m sub l value of +1, and either forming a net m sub s of 1, because everybody's pointed up, or 0, as everybody cancels out. Then I can take these configurations and flip my first electron, which means that I'll have a m sub s of 0 and an m sub s of -1. Now, as you can imagine, we've got one last final state, and it should be hopefully obvious. I can have both my electrons paired up in my third p orbital. So this is again where m sub l is equal to +1, which gives me 2 electrons the uh, in the m sub l +1 for a total orbital spin of 2 and no net spin angular momentum. So I just generated a lot of different states and a lot of m sub l and m sub s values. So how can this be helpful? Well, what we can do is try and count the number of times any given combination of m sub l and m sub s occurs. So some cases occur once, some cases as many as 3 times, 1, 2, and 3. So we'll put this in what's called a square diagram, where I list my m sub l values on the left and my m sub s values along the top. And if something doesn't occur at all, like I never have a state where m sub l is equal to 2 and my m sub s is equal to -1, I give it a 0 value. But if something occurs multiple times, like both m sub l and m sub s being 0, then I'll give that how many times I observed it, 3 times. So if you need some time to go ahead and count out your orbitals to complete the square diagram, please feel free to take a break. But once I have this diagram, I can use this to help me diagnose what term symbols I can combine together to give me this general pattern. So a very good place to start is finding what your largest value of m sub l is, and then making use of a trick we've brought up previously, which is my largest value of L has to be the same as my largest value of m sub L. So this means if I have an m sub L of 2, I have to have at least one term symbol where L equals 2, and I can't have any term symbols where L equals 3. So this is actually fairly useful. Then, looking at this guy, I know that if L equals 2, I can't have an m sub s of positive or -1. I only have an m sub s of 1, which means when L equals 2, the largest value of m sub s I can have is 0. So my largest s value is also going to be 0. So putting this together, that means that I can have a term symbol of d when L equals 2, and a multiplicity of 1 or a singlet state because s has to be equal to 0. So I now know that at least one of the possible term symbols in silicon is going to be this singlet d state. Now, in order to figure out everyone else, I'm going to want to take my diagram for my total and subtract out a square diagram that corresponds to the singlet d state. And in this case, I know that for a singlet d state, m sub l values can go anywhere from positive L to negative L, or 2 to -2. But m sub s has to go from negative s to s, or has to be 0 for a singlet state. So this will be my square diagram for a for the singlet d state. So I can go ahead and take my initial starting square diagram that I figured out, subtract out my singlet d, and what I get left is a much smaller diagram. Now, this guy is going to be composed of some other subset of diagrams, so I can use a similar trick. So when I do this, I'll find that the maximum ebb sub L that's left is 1, which means of my remaining term symbol, the largest L value is also going to be 1. But for this term symbol, I can have m sub s values ranging from negative to 1, which means that I've got an L of 1 and an S of 1. Well, this means that my remaining state contains a triplet P, where S is 1 and L is 1. So we can go ahead and construct our diagram for that. And what I end up with is 1s in this entire area. So when I subtract this guy out, all I'm left with is a single state with an m sub s of 0 and an m sub l of 0. Well, there's only one state that has that, and that's going to be a singlet S state where S equals 0 and m sub l, and L also equals 0. So when I diagnose my diagram, I find that it contains 3 possible term symbols: a singlet D, a triplet P, and a singlet S. So that gets me a large way towards the problem. But there's one last component of my term symbol that's missing. That's going to be our J values. And for that, Russell-Saunders comes into the rescue. So if you need a refresher on that, I encourage you to go back to total angular momenta, and you're going to find that for Russell-Saunders coupling, our J values can go anywhere from L plus S to L minus S. Well, for our singlet D state, L equals 2 and S equals 0, which means we've got no spin orbit coupling, so J has to equal L. So this means that our only possible state is going to be L equals 2, S equals 1, J equals 2. That's going to be the only possible J value for our singlet D state. Now, if I try and expand this idea to our triplet P, this gets a little bit messy, because in this case, I have an L of 1 and an S of 1. So I can have 3 possible J values. Either my L and S add together for a J of 2, or they take the difference of L minus S and a J of 0, and of course, any integer value in between. So I have 3 possible term symbols for my P state: a triplet P with a J of 2, triplet P of a J of 1, and a triplet P of a J of 0. But we're not done yet, because we still have our singlet S. However, in this case, I have no angular momentum, because L and S both being equal to 0 means that J also has to be equal to 0. So when I put this all together, I find out that I have 5 possible term symbols. Now, if you go back to when we did the same problem in total angular momenta, you'll find that we originally proposed 10. And that's because what we left out previously was how our spins and our orbital angular momenta interact. Not every combination turns out to be possible. So when you're dealing with 2 or more electrons in a P, a D, or an F shell, I highly encourage you to take the time, use the slower process, figure out your microstates, and make a square diagram. So this process is going to be very universal, but it can take a lot of time for bigger systems. So try and give yourself some practice. So that brings us to the end of the basic introduction to term symbols and how we can determine this for almost any atomic species. However, now we're left with an interesting question. I know that silica has one of 5 different term symbols, but which one's the lowest in energy? For that, I'll see you next time. Take care and stay healthy.